All right, everybody, welcome back to part 2 of our notes for this unit. And this part of our unit is going to focus on gas stoichiometry. And remember, stoichiometry is my favorite. So let's just remember the thing, or just general steps for any stoichiometry problem is that you're going to start with a balanced equation. Sometimes that will be given to you. Sometimes you will have to do that. All right. Determine what you are looking for. It's always a great idea to write the label of that at the end so you know where you are going. Determine what information you're starting with. You're going to be given a lot of numbers in these problems. And remember that you have to figure out exactly where you are starting. You're going to then factor label to get your answer. I'm sad that I'm not going to be able to see a lot of your factor label, but please remember that is the best way to do that. And then, of course, we are going to be dealing with some sort of gas law, either at the beginning or the end of your stoichiometry problem. This is the gas law unit after all. Now, the simplest type of gas stoichiometry deals with situations when you're at standard temperature and pressure. Because at standard temperature and pressure, we have a conversion to go directly from moles to volume. Again, this is great, but you can only use it when you're at STP. Let's see what this looks like. What volume of hydrogen gas at STP can be produced when 5.54 grams of zinc reacts with excess hydrochloric acid? All right, so I have my balanced equation. Fantastic. I'm starting with my 5.54 grams of zinc. I want to get to, I asked for volume, so that's going to be in liters of hydrogen. I took my mass of zinc, I converted it to moles using the molar mass from the periodic table. I then went from zinc to hydrogen. Anytime you go from one substance to another, you have to have a mole-to-mole relationship, and I got that from the coefficients in the balanced equation. Now, because I'm at STP and it's a gas, I can go directly from moles of hydrogen gas to volume of hydrogen gas because 1 mole of any gas at STP has a volume of 22.4. Right? I then plug that in and I end up getting 1.9 liters. All right, why don't you guys go on ahead and do the next problem on your own? Okay, and you can pause this video and then we can show you the answer. All right, great. So let's look at our next one. We are taking sodium, reacting that with chlorine gas, and we're going to get sodium chloride. What mass of sodium chloride can be produced from the reaction of 112 mils of chlorine gas at STP and excess sodium? All right, great. Now, remember, excess sodium means I have plenty of it. Had I given you the mass of sodium, then that would have been a limiting reactant problem. And that's certainly fair game, so don't forget that that's out here. All right. So I have my volume in liters, converting that to moles. Because I'm at STP, I can use 22.4. Converting from moles of chlorine to moles of sodium chloride. 1 mole of sodium chloride, 58.5 from the periodic table. Get about 0.585 grams as our answer. All right. Fantastic. Okay, so not all of our problems are going to be at STP. And if they're not, that means that you have to do a little bit more work. All right, so no more STP. I have 35 grams of water decomposes into hydrogen and oxygen gas. There's my balanced equation. What volume of oxygen will be produced at 120 kilopascals and 200 degrees Celsius? So right there, I see I am not at standard temperature or pressure. So I cannot use 22.4. People get into the habit of wanting to use that too much. You cannot. So instead, what I'm going to do, I'm going to start with my mass of water, which is what was given to me. I'm going to convert that to moles. I'm going to go from moles of water to moles of oxygen. I'm going to stop here. I'm now at my moles of oxygen. What do I want? I want to know what volume of oxygen. Well, I don't have a conversion directly from moles to liters, but I know if I find my moles of O2, I can then use the ideal gas law to find the volume because I have my pressure, I always have R, I have my temperature, and now you have your moles. So you've done a stoichiometry problem, and now you're going to use the ideal gas law to solve for volume. All right, because again, you cannot use 22.4 if you're not at STP. All right, going ahead and do the octane problem. You can pause if you'd like. Okay, I'm just going to go on ahead. What mass of octane at 50 degrees and 75 kilopascals of pressure is necessary to produce 250 mils of carbon dioxide? All right, well, I gave you a little tougher one to balance here, but we remember combustion reactions. In this case, I'm giving you a volume, all right, to start out with. I'm not at STP. So in this case, I'm going to start with my ideal gas equation, and I know the pressure, I know the temperature, I know the volume. I'm going to figure out how many moles that is. So I plug my numbers in, I figure out how many moles of carbon dioxide. I want to know what mass of octane I can produce from this much carbon dioxide. All right, well, I'm at moles of CO2. I can then do a mole to mole ratio based on my balanced equation. 1 mole, all right, of octane is 114 grams. And then I end up getting about 0.0998 grams. So this is an example of where you're using the ideal gas equation first and then doing stoichiometry second. All right, either will be, you will be asked either of those. All right, okay. Next up, limiting reactant problems. We remember these, all right? Limiting reactant means that you are going to have to deal with an amount of each reactant, and you're going to see which one produces the smaller amount. I don't love this example I have in my notes here, so you'll see some limiting reactant problems in your practice, and make sure you take a look at those. All right. Final thing we're going to talk about for this unit. So we're almost done. All right. We're talking about ideal gases. It's called the ideal gas law. And ideal means that the gas itself, we consider that it has no actual volume. The only volume we consider is that of the container. We also say that for an ideal gas is actually that those molecules don't have any attraction for each other. Well, neither of those are true. There is a volume, although small, and some gases can be very attracted to each other. All right. For the most part, doing these ideal gas equations works fine, but know that as you can have conditions where real gases start to really not quite act ideal. And down here kind of tells you, real gases differ most from an ideal gas at low temperatures and high pressures. Well, what's happening under that situation? Low temperatures means that you're slowing those molecules down. If you're slowing them down, the attractive forces can certainly work more, all right, which is going to end up impacting your calculations a little bit. High pressure, you are forcing those gas molecules closer together, again, increasing the chance of those intermolecular forces becoming a little bit stronger. All right. Now, for our purposes, and really for purposes through really most of college chemistry, gases can be treated as ideal, but just know that there is a difference between an ideal gas and a real gas. All right, guys, so at this point, you should do your gas stoichiometry practice. The answer keys will be under the modules, and I hope you enjoy the labs and all of the reviews and everything else for this unit, okay? Please feel free to give us an email if you guys have any questions. All right, take care.